Here we go. So today we're going to be talking about three-dimensional figures, and the whole reason that we worried about the area of two-dimensional figures is to kind of help us figure out three-dimensional figures. Because yes, finding the area and finding like certain parts of 2D figures doesn't really help us much in the real world, considering we live in a three-dimensional world. But we can use those ideas to help us figure out the best way to look at 3D objects, okay? Because if you think about it, a lot of 3D objects are made up of 2D surfaces, okay? And you'll see what I mean in a minute, okay? So there's two different types of 3D figures. One is called a polyhedron, and the other is called a non-polyhedron, okay? And so the ones that we're really going to be focusing on are polyhedrons, okay? So what a polyhedron is, right? It's a figure enclosed by flat surfaces, and these flat surfaces are what we call faces, okay? We have two different examples of these. We have what's commonly called a prism, and we have what's called a pyramid, okay? And you can see that we have a lot of different looks as far as kind of like what they can kind of look like. And prisms, hopefully you've seen before, if you've ever actually had a prism that bends light and so on and so forth. It's the same kind of idea. It's just one type of prism. Prisms actually extends a little bit more, and we'll talk about that in just a minute. And then pyramids, of course, you've seen things like the pyramids of Giza, so on and so forth, okay? So some real-world examples of polyhedrons might be like a pizza box, a dresser, a cabinet. So even though those shapes don't really, like when you think of the word prism, those shapes don't really come into mind, is that the fact is they're actually composed the same way that a prism or a pyramid are, okay? I'm sorry. Then you have what's called non-polyhedrons, okay? And so non-polyhedrons, right, are figures enclosed by curved or non-flat surfaces. Okay, and the examples that we're going to look at, right, are cylinders, cones, and spheres. Okay? So, and you've seen all these different shapes before. I mean, think about a cylinder. How many of you have ever had a soda before? Right? Drink out of an aluminum can. This is a cylinder. Okay? Cones. How many of you have eaten an ice cream cone before? Boom. Or a snow cone. Right? Boom. Okay? And then spheres. How many of you play sports? And play sports with a round ball? You work with spheres all the time. Okay? So some other real-world examples of non-polyhedrons, for example, baseballs, soda can, bottle, a roll of toilet paper, right? Or paper towels. Those are some real-world examples of cylinders, spheres, or cones. Okay? All right. So we're going to look at prisms and cylinders today, okay? That's our big emphasis. And the reason why is because they're actually very similar. Okay? So prisms, some key features. Okay? The prisms, what they are is they're made of two parallel and congruent bases, okay? So there's two different parts to them. So the bases, so if you look at this, for example, this hexagonal prism, okay? The way that these guys are made, there's two parallelogram congruent bases. Then the faces, or the sides, are they're all parallelograms. Now, they may not be rectangles. Most of the time that we're going to use them, they will be, but they can be just any sort of parallelogram. And then use shape of base followed by the word prism to identify, okay? So when you say this hexagonal prism, right, that should be your indicator that this hexagon, right, would be my base, okay? And these rectangles or parallelograms right here, these are what we call our faces, okay? Another example would be a triangular prism, okay? So again, I've got my triangle bases, and then these parts right here, right, are called my faces. Right, so if I look at a hexagonal prism, for example, I've got a base on top, hexagon, and then it doesn't really show, but I've got a hexagon on bottom too. Okay. How many faces do I have? 6, right? So the base is going to tell me the number of different faces I have. Okay? So another example would be like an octagonal prism. Okay? So here I have an octagon up top. I have 8 faces, right? And I've got an octagon on bottom. So if you kind of look at this, it kind of looks like a drum, right? Kind of looks like a drum. That's the perfect example of kind of what a prism really looks like. Okay? Now I know some drums don't actually have a bottom, but prisms do have a bottom. They have a top and a bottom. They're both called bases though. Okay? Then we have what's called cylinders. Okay? The cylinders, right, the difference between a prism and a cylinder is the cylinder has 2 congruent and parallel circular bases. So automatically we know that the top and bottom are always going to be circles. Now, the bases are connected, instead of having faces like the drum did, right? They're going to have one long, smooth, curved face. Okay? Now, again, this is kind of like a way of thinking about this in terms of like calculus, and so to speak. So it's basically a circular prism, or a prism that has an infinite-sided basis. And so what I mean by that is, if we notice that this octagonal prism, it's starting to look more like a drum, but drums are circular, right? So if I just keep adding sides, and again, we're focusing on having regular polygons up here, okay? If I have a decagonal prism, right, so we have 10 sides, you'll notice that it's starting to look more round, okay? The more and more sides I add, the rounder this thing looks. So if I just said, hey, you know what, we're going to use an infinite number of sides, right, that kind of becomes a cylinder. So that's why prisms and cylinders we really focus on as the same type of idea, because realistically, they are the same. Just for prisms, right, I have to consider all my different faces. For cylinders, I don't necessarily. I'm thinking about one long, smooth face. Okay? All right. Again, this is just kind of an introduction. So these are what we're going to be looking at today, but I also want to show you, if it'll let me go. Oh, that's it. That's the end of it, right? Okay. Okay, that's just for today. So we'll talk more about pyramids and cones. Pyramids and cones tomorrow. Okay. Ow, that just hurt me. So now I want you guys to get out a sheet of paper, all right? Because we're going to be looking at what we can, different types of measurements that we can make on prisms and cylinders. Okay. I'll give you guys just a minute to kind of get everything ready. And I'm going to take attendance while you guys are doing this. All right, and so for the sake of today, we're really just going to be looking at, we're going to talk about these prisms and stuff like that, and these cylinders, and we're going to look at just one aspect of this. So you see a couple different ideas in here, right? We're just going to discover kind of where these formulas come from, okay? And then we're going to kind of go through an actual example. All right, so here we have a right prism. Now, before I really get to kind of talking about different parts of this, I want to identify those parts that I just mentioned, right, in my presentation. Okay, so here we have a prism, right, and when we say bases, right, what we're talking about, or what shape is our base here? What do you guys think? What shape? What's that? It's a pentagon. So this is what would be what we call a pentagonal prism. Okay? And the reason it's called a pentagonal is because my bases are pentagons. So here we have my base up here. All right, one second. And my base down here. Now you'll notice that there's dotted lines on here. So I don't know if you guys have ever seen kind of 3D representation. Those dotted lines mean that those lines are there, but we just can't see them. Okay, so it's just a representation of, for example, like if I hold up this Monster can, right? On the back there's things like the nutrition facts, but you can't see them, right, when you're looking at it. So the dotted line represents, hey, this stuff is here, you just can't see it. Okay? And so these two parts, these two pentagons, oh shoot, I keep missing my, right? These are our bases, okay? Now, in order for them to be a prism, right, these bases, right, they have to be, well, for the sake of what we're going to calculate, they need to be regular, but more specifically, they're congruent, meaning that this side, this side, this side, this side, this side is still congruent to this side, this side, this side, this side, and this side. Okay? Now, when we talk about their faces, right, you'll notice here that we have all 5 of these parallelograms here. Okay? Now, each one of these things, right, is called a face. So the parallelograms are always going to be my faces. Okay, so now remember, they're parallelograms, which means a couple of things. One, we know that these two opposite sides, the top and bottom, are already congruent because they were for the bases. But we also know that these pieces right here are not only congruent, but they're parallel. Okay? We also know that these sides up here are also parallel. Okay? So actually I'll make double picture these. But more importantly, right, what you're going to start to see is because we have this regular shape here, right, each one of these faces, so each one of these the other sides of my faces, right, these are also congruent and parallel to all other sides of those. Okay? Now, the reason that this is called a right prism, okay, is because each one of these faces are actually rectangles. Okay? So which means that they meet my faces, right, perpendicularly. So that means these are all right angles. Okay? And that's why it's called a right prism. Okay, so that means that each of these faces in this case are all rectangles. Now, I mean, I can have, for example, I can actually have a shape that maybe looks more like this, I can have a prism that looks like that, right? And all the same things are still going to apply. The only difference is now when we're dealing with a parallelogram, right? We have to consider, all right, I need to find this height here in order to calculate the area of that parallelogram, okay? And that's really the only difference, okay? And I'll explain why we might do something like that in just a second. All right. So today we're going to be talking about, for both prisms and cylinders, we're going to be talking about what's called surface area, okay? And surface area is the total area of the surfaces which make up a 3D figure. Now the key word in that is area. Okay? So we just spent a couple of weeks talking about how to calculate areas of certain or of different types of figures. Okay? So for this one, we're going to develop, okay, well, how am I going to be able to come up with a formula for prisms? Now, the reason that this is going to seem a little bit more like formulaic and more of conceptual instead of actually like, hey, this is how you calculate it for all prisms, is because, right, yes, this is a pentagonal prism, but clearly you can see that if I want to find the surface area of, let's just say, a triangular prism, right? You'll see that in order to calculate the area of my base here, it's going to be different than if I would calculate the area of my base here. Because this is a triangle, this is 1/2 base times height, and for this pentagon, it's 1/2 my apothem times the number of sides times the length of one side. Right? Come on in, bud. So I've got lots of different ways that I can actually do this. So we're not going to look at this so much as in, again, formulaic, as in this is how you do it for each one. We're going to look at this more of like, okay, conceptually, how might I approach this problem? Okay. So we're going to use, there's a couple different ways that people identify surface areas. So what we're going to use is I'm going to use SA, okay, my surface area, okay? So in order to kind of figure out how the total area of this thing, I want to look at, well, my base areas, okay? In this figure, right, I've got two bases. I've got the top, right, and I've got the bottom. And we know that they're both congruent because of the definition of what a prism is. Okay? So what that means is if I think about this, okay, depending on the shape, the way that I calculate the areas of the bases are going to be different. But if I say that the base area of one of these, let's just call it, is B, right? And I've got two of them, right? That means in order to find the surface area, the first thing I need to look at is, well, I don't need to calculate the area of both of these. If I have one of them, I've got them both, essentially, right? It's just double. So the way that we can calculate surface area first is all I do is I take 2 times my base area. Does anyone else hear that feedback? Yeah. Can you shut the door? I don't know who's driving me crazy. So much better. Okay. So far what we have in order to calculate the total, and again, the idea of what surface area means. So if I think about, how many of you have ever wrapped a present before? Right? So if you notice when you start off with the wrapping paper, it's just one flat piece of paper. But you put your object inside and you fold everything kind of around it, right? Surface area, right, is how much wrapping paper you actually used to cover the entire shape. Okay? So that's what that means. That's surface area. Okay? So we're going to break that up, and if you think about the surface area, or that surface area, how much wrapping paper you need, well, I need the, whatever sides I've got here, I need the top and bottom, and I need the left and right. So I need all those measurements. Right? And that's exactly what we're going to be calculating here. Okay? So the next thing that we have is what we call lateral area. Okay? And lateral area, what does that mean? This is the area of all the faces. Okay? All right? This is the area of all the faces. Right? And we're going to use L to write this. So, but let's kind of break this down even a little bit more. So, if I have lateral area here, right? If I look at each one of these faces here and I just kind of take them and I go, and I pop them out, just kind of like we did with the bases, I've got 1, I've got 2, and again, pardon my inexact, 3, 4, 5. Okay? And I know they look terrible, right? But when we look at these, when we take these faces out, we're going to notice that, well, I know all these parts are congruent, right? Because all of these are my sides, right? These are the sides of my bases. Okay? And I know all of these parts are congruent too, right? And if you think about it, otherwise this shape wouldn't really form right if I had different heights. So imagine if, again, just imagine if this side was shorter than this side. It would just be all awkward and really work, right? So my sides have got to be the same. So essentially, if I think about my lateral area here, okay, call it L, right? If I look at the area of each one of these things, well, the area of this one is base times height, right? Which is this part right here is my base. This is my height, right? And I've got base times height, base times height, base times height, and base times height, okay? Well, how many different base times heights are there? 5, okay? So the total area for this one would be 5 base times height. Well, if I look at, what's 5b? If I just look at 5b, right? 5b. This is my perimeter. It's the perimeter of my polygon, right? Yeah? So another way of thinking about this is the perimeter of my bases times my height, okay? So for lateral area, it's always perimeter of bases times the height of my parallelograms, okay? So I'm going to make a little note here. P is, hold on, let me make it a little more definitive, okay? Where P is perimeter of base, okay? So, another way, so again, the perimeter of the base is going to depend on what the actual base is. So if we're just kind of thinking generic here, the way that we calculate surface area is double the bases, because I know guaranteed no matter how many sides it has, there's going to be exactly 2, right? And then add in whatever my lateral area is, okay? All right. So we're not going to talk about volume at the moment. So here we have an example. First off, identify what type of shape is this? What? It's a triangular prism, right? So this shape right here is a triangular prism. Oops, sorry, I don't know why that came out. Okay. Now, the way that we're going to calculate this, and again, we don't have much information, so I'm going to go ahead and just give you some pieces of information. I'm going to say that, I know, why is this? All right. This side here is going to have a length of 4, and this side here is going to have a length of 3. Okay? Now, since this is a right triangle, okay, first thing that we want to do, and I need my height, which is 10. Okay? So, in order to calculate the surface area, remember, come on, move. Remember that surface area is equal to 2 times the area of my base plus my lateral area. Okay. So first thing we want to do is let's calculate my base area. Let's find B. Okay, let's find what B is. Okay. So since this is a triangle, my base area is equal to 1/2 my base, which in this case is 3, or 1/2 3 times the height of my triangle, which in this case is 4. Okay? So, since again my B is going to equal 3, and my H is going to equal 4. Okay? So, the area of this triangle then is 1/2 12, which is equal to 6. Okay? So far what I have is this is 2 times 6, and then we need to find what the L is. Okay? All right. So remember now that L, lateral area, is equal to the perimeter of my base times the height of my whole object. So we already know that the height of the whole object is 10. Okay? We now need to figure out, well, what's the perimeter of my base? Okay? Well, the problem is I can't do this necessarily. Right? Because I only have 2 pieces. But remember, the top is a right triangle. So if I'm going to pop out this right triangle over here, okay, this is a length of 3, this has a length of 4. Remember that in order to solve this part, let's just call this C. Right, and since C is my hypotenuse, the Pythagorean theorem tells me that this is 3 squared plus 4 squared has got to equal C squared. So understanding that when you're doing surface area, right, sometimes it's going to take a lot more steps than just simply plugging it into a formula. It's a process, okay? And so we need to make sure that we're working through this process, okay? And I'm trying to show you the steps that you need to kind of take. You start with the base area. Then you work on the lateral area, and always work in that fashion. The base area may be more complicated, right? For example, that pentagonal prism, right? We would need to find the apothem first. We might need to do some trig, right? There's lots of different things that we might have to do, okay? But let's continue on with our triangle here. Then I get 3 squared plus 4. And hopefully by now you saw that this is actually a Pythagorean triple. Okay? But let's just go ahead and continue. C squared. 25 is equal to C squared. Take the square roots of both sides, and I get C is equal to 5. Okay? So since C is equal to 5, my perimeter then becomes 3 plus 4 plus 5, which is equal to 12. Right? So then my lateral area becomes 12 times 10, or 120. Okay. Making my surface area, since L is now 120, this makes it 6 times 2, which is 12 plus 120, which is equal to 132 units squared. Okay. And that's how you calculate surface area. Okay. My screen is frozen? On. Is anyone else having that problem on Zoom? That my screen is frozen? What? It's frozen? How in the world? Here. I'll stop sharing and then try sharing again. I don't know why I did that. I apologize. I don't know. There's no reason it should have done that. And I couldn't even tell that it did. Okay. Again, maybe if you missed a lot of that part, please go back and watch this video so that you can kind of fill in those holes. I know you heard what I said, and I know some of you have been following along if you're in class, but those of you on Zoom, I apologize. Please go ahead and watch back through the video in order to kind of see. Okay. All right. So that's for surface area of prisms. Okay. It's going to be a little bit easier, actually, for cylinders. Okay? So again, this is what we call a right cylinder. And the reason it's called a right cylinder is because, right, it's not obscured. It's not like, it doesn't look like a bunch of dimes that are stacked and about to fall over. It doesn't look like anything like that. It is straight up and down. It looks like a can. Okay? So, for surface area for these guys, there again, we're going to develop the formula for this. Okay. First thing I want to do, right, is understand how am I going to do this. Okay? So let's just talk about the base area first, just like we did with prisms. Okay? So again, this is a circle, the top and bottom. Oops, sorry, I used blue for that. Okay? And I know that this bottom has the exact same shape as the top does. Okay? So, again, parts of the circle that we kind of usually need is we either need diameter or we need radius. Okay? So if I'm looking at just the base area, okay, again, there's 2 circles. And I'm sorry, my circles suck. Okay? They're 2 circles with the exact same radius. Okay? Meaning that they're congruent. Okay? So if I think about this, if I think about the base area of just one of them, right? If I think about just B in general, right? What's the area of this? What's the area of one of the circles? That's the total degrees. 360 is the total degrees. What's the formula for the area of a circle?
2r times pi.
2r times pi, that's actually, it's close, that's circumference. 2 pi r is circumference. So which one's area? We're almost there. Pi r squared, perfect, there we go. So the area of one of these guys is going to be pi r squared. Now the formula for this is going to look different, but understand it's the exact same as for finding a prism. I take the 2 times the base area, and I take my lateral area. Right? That's all we need in order to calculate this thing. However, the lateral area and the base area are going to look a little bit different. Okay. So for this, for the surface area of a right cylinder, right? If it's 2 times the base area, and the base area of one of them is pi r squared, we can actually be more specific for this one and say, well, this is guaranteed going to be 2 pi r squared, because it's double one of the base areas. Okay? Now let's look at the lateral area, though. Okay? So this lateral area is going to seem a little bit different because the last one we had a bunch of parallelogram faces. And so it was really easy to calculate what each parallelogram was. If I want to take a visual of what this face looks like in 2D, if you think about a can, okay? If you think about, for example, like slicing this can straight down, right? And then unwrapping it, what shape do you get? You get a rectangle, right? If I think about just literally slicing this thing down and unfolding it, right? That's another way of thinking about this. Okay. If I've got this circular piece of paper here, and you can see it's a circle, it's a cylinder, right? And these are my sides. If I unwrap this thing and I unroll it, I get a rectangle, right? And that's the exact idea of why this works. So my lateral area, or my face, actually looks like, just instead of a bunch of parallelograms, it's just one big parallelogram. It's actually even more. It's one big rectangle, right? Now, the height of this thing, okay, we're going to always need. But how do we find that top part? How do we find that other dimension? Since the area of this guy, of this piece right here, is equal to base times height, the problem is we need to find what this base is. Okay? Hold on. Height times diameter. Not going to be height times diameter, right? So the thing so she's saying, like, hey, if I take this whole thing, right, that's the diameter, and then it'll be the height. The problem is, right, like, for example, on this can, right, the distance around, like the length of it, if you think about the sides, I start here, and I unwrap all the way around, right? I didn't go the diameter. How far did I travel? The circumference. Perfect. Okay? So, the length of the top of this is actually the circumference of this circle. Of the top circle. Okay? Now remember, circumference, as we stated before, as Zach said before, is actually 2 pi r. Okay? Sorry, my L's and C's look the same. Okay? So the lateral area for this guy, since my B is the same thing as my circumference, so the lateral area is actually going to be 2 pi r times my height. Okay? And so that's where we finish the formula by now adding to our surface area 2 pi r squared plus 2 pi r h. And for those of you that want something even simpler, right? This is the same thing. I can factor out 2 pi r from each of these, right? They both have a 2 pi r. This would be the same thing as 2 pi r times r plus h. Okay? But more importantly, this is the one that I want you to use. Okay? So now let's look at an example of this one. I've got to put my dimensions in here. So let's just say the height of this guy. So here's my radius. Let's just say my radius is 2. Okay? And then my height right? Let's just say that this is 4 and so on, so you can kind of see. So again, height, like again, I represented it before. Oops. I represented it before using the side, right, going out here, okay? But understand that it's the same as the distance from the center of the top to the center of the bottom. So there's 2 different ways that we represent it, okay? So now, remember, now I've got, the beautiful thing about cylinders is I've got all the pieces I need now, okay? So our surface area, remember using our formula, is going to be 2 times pi r squared, because 2 times the area of one base, plus 2 pi r, my circumference, times my height. Okay? And so this is 2b, and this is my lateral area. Okay? So let's calculate them out first. Okay? So my base area is equal to pi r squared. Well, r in this case is 2. So this is pi times 2 squared. And 2 squared is 4, so this is just simply 4 pi. So then 2b would be equal to 2 times 4 pi, which would be 8 pi. Okay. My lateral area is 2 pi RH, right? And so now I know that R is equal to 2, H is equal to 4. I know my lateral area then is equal to 2 times pi times 2 times 4, which is 2 times 2 times 4, which is 16 pi. Okay. So for my surface area, right, we already know that 2 pi r squared is 8 pi. And we know our lateral area is 16 pi. Okay. That gives us a total area of 8 plus 16, which is 24 pi units squared. Okay? Does that make sense? Whew. A lot of problems, okay? Any questions on this? Now remember, again, one of the things that I want you to remember is that the triangular prism, yes, it was a lot of steps, and it was easy for us to calculate because, right, it was a simple triangle. Not all shapes are going to be simple. Remember that in order to find the area of the base, you have all those formulas that we just learned. Like for the formula for the area of a regular polygon, or the area of a triangle, or a parallelogram, or a rhombus, kite, trapezoid, all of those. Right? You have to remember those, right? And you have to use those in order to find the areas of the bases. The faces are easy. It's the bases that are going to trip you up, so please make sure that you're focusing. Okay? Any questions? All right, I'm going to go ahead and stop the video.